The modern data center is an environment of extreme energetic density. In a facility like this, actual flame spread is only one of many catastrophic threats. Airborne smoke contamination, accidental liquid release, and the abrupt loss of cooling can destroy IT hardware as efficiently as a fire. To survive an event, data center fire protection cannot be a standalone reactive tool. It must operate as a deterministic, engineered ecosystem. This chart shows every design decision maps back to three overarching objectives: life and responder safety, property protection, and service continuity. These goals often conflict. The owner must explicitly define the residual risk accepted for each pillar. Undocumented or ambiguous protection logic creates hidden failure points that lead directly to the top event: a catastrophic loss of critical IT service. Achieving actual reliability requires bridging the gap between standard life safety codes and the extreme physical realities of energized IT infrastructure. That bridge is built on a spatial architecture called defense in depth, designed to eliminate single points of failure. Every critical objective requires at least one layer of prevention, detection, mitigation, and a planned recovery path. Applying generic fire codes across a whole building ignores the unique hazards of specific IT zones. The diagnostic matrix for a standard data hall reveals a challenge. They have medium fire growth potential, but very high sensitivity to smoke and interruption. Contrast that with the row for a lithium-ion energy storage system. The primary ESS risk is thermal runaway, resulting in toxic deflagration. Managing this event requires active exposure cooling and dedicated venting to prevent structural spread. Applying the wrong mitigative barrier to a specialized room can trigger a cascading facility outage rather than containing the fire. We can deconstruct how these layers coordinate by following the timeline of an incipient cable fault inside a high airflow data hall. At T+0, a loose PDU connection begins heating a cable. This pyrolysis produces invisible particulate matter long before an open flame appears. Traditional ceiling-mounted spot detectors are ineffective in this specific environment. Extreme cooling forces alter the basic physics of a fire. 60 air changes per hour of cold supply air will force a thermal smoke plume downward, flattening it and preventing it from reaching the ceiling. As this diagram shows, detection systems must be engineered to physically follow these forced airflow paths directly into the return air grills. Aspirating smoke detection, or ASD networks, constantly sample these return air streams to catch invisible pyrolysis particles the moment they are generated. The FM Global Datasheet 532 benchmark confirms this. Airflows greater than 1.5 meters per second require these early warning sampling systems. Detection must automatically interlock with the HVAC system to reduce airflow, or the active suppression agents will simply be blown away. Moving down the timeline to T+3 and T+5, the system reaches the escalation phase. A single alert should never trigger suppression. Instead, the signal must pass through a linear deterministic circuit to be verified. The input hits verification gates, such as cross-zoning multiple sensors and coincidence timers, to definitively eliminate false positives. Once verified, the logic falls to the fire alarm control panel, the ultimate source of truth in the facility. This panel operates with local autonomy, ensuring that critical functions survive even during a total facility network loss. Its life safety logic holds absolute priority, preempting routine BMS and HVAC controls. The panel then executes pre-programmed fail-safe outputs, automated voice evacuation, damper closures, and direct brigade dispatch. Every digital input requires a defined, pre-programmed output. A deterministic system never acts ambiguously. At T+7, the physical suppression response reaches its ready state. This chart compares response speed and complexity between wet pipe and double interlock pre-action systems. Engineers select double interlock systems to prevent accidental water discharge over energized racks, despite slow fill delays and high maintenance burden. Opening the main suppression valve requires a specific sequence of logic centered around a mechanical AND gate. In Pathway 1, the ASD unit confirms smoke, signaling the control panel to energize the solenoid on the valve trim. Simultaneously, in Pathway 2, heat from the fire must break a sprinkler bulb. This causes supervisory nitrogen pressure to drop, opening a pneumatic actuator. If smoke is detected but there is no heat to break a sprinkler, the valve stays closed. If a pipe is damaged but there is no smoke, the valve stays closed. Both conditions must trigger together. Total flooding clean agents are often preferred for electrical rooms to avoid liquid damage, but they carry a crucial limitation noted here. These systems rely on perfect room enclosure integrity to maintain the required gas concentration. A leaking door seal causes the system to fail. Even with a perfect enclosure, these agents offer minimal thermal cooling. Deep-seated, energized thermal faults will immediately reignite once the agent dissipates. Gas discharge alone is an incomplete protection strategy. Once the fire is out, the post-event recovery phase, safe isolation and atmospheric purging, relies on the system acting exactly as it was originally commissioned. Proving that design reality requires following the NFPA 3 and 4 commissioning sequence, culminating in G5, the Integrated System Test. The Integrated System Test is the ultimate crucible. It forces end-to-end scenarios to verify that the chronological sequencing executes properly. The test must intentionally force abnormal failure modes, like a device dropping offline or total power loss, to prove that the fail-safe states hold. A system's reliability begins degrading the exact moment commissioning ends. To combat this, NFPA 25 mandates strict ongoing functional testing for water-based systems, including specific triggers for fire pumps and their controllers. Testing these assets is a violent mechanical reality. High-capacity pumps must be spun up rapidly to prove they meet their hydraulic flow curves without degradation. If any single component in the chain, an ASD unit, a damper, or an actuator, fails its periodic test, the entire facility is exposed to catastrophic loss. Chronological, documented testing is the only proof that the system will perform tomorrow identically to its day one baseline. Human element impairment and unmanaged bypasses represent the most significant threat to a fully commissioned facility. Prohibited practices include undocumented software disables, unapproved isolations at the panel, and leaving physical valves closed without tags. Managing these risks requires a named risk assessment, active temporary fire watches, and an end-to-end alarm confirmation upon restoration. Evidence retention functions as a critical component of the physical protection system, tracked through specific metrics like ITM on time and deficiency aging. Missing or falsified testing records are an operational defect, hiding silent configuration risks until it's too late. Ultimately, all facility operations answer to an absolute legal hierarchy. Internal uptime certifications or the preferences of the owner never supersede the statutory fire code or the final approval of the local authority having jurisdiction. In the eyes of the law and against the physics of a fire, undocumented protection is no protection at all.